wonderful to be here. My name's Trish Hansen. I am the founder of Urban Mind Studio and the moderator of today's session. Please welcome, find your way in, find a seat. I'd first of all like to thank the Dubai Future Foundation for the incredible opportunity to have this important and complex conversation. It's a real privilege to be here with our esteemed panelists, scientists, practitioners, clinical practitioners that spend their lives thinking deeply and thoughtfully about this conversation we're about to have. Now, to manage our expectations, we do have only 45 minutes. So there's one promise I can make to you, and that is that you will leave with more questions than answers today. So I'll ask the panelists to introduce themselves because your CVs are so extraordinarily long and convoluted and wonderful. But here we have Mohammed Udin, we have Dieter Elgi, and we also have Matt Pryor. So I might start throwing to you, Mohammed, because you are based here in Dubai, to introduce yourself. Tell us a bit about your work and also some of the things that motivate you about your work. What's exciting? What do you think is coming? And why you do what you do?
Thank you, Trish. So I would also like to thank Dubai Future Forum for arranging such a nice event. So I'm a geneticist, work at the Mohammed bin Rashid University of Medicine and Health Sciences. We are part of Dubai Health. So my lab actually look into the genetics of neurodevelopmental disorders. So, you know, if you look at autism spectrum disorder or intellectual disability or epilepsy, these conditions are caused by genetic mutation. And this genetic mutation eventually disrupts the cognitive function and also sometimes the physical activities. So these are devastating conditions that require proper diagnosis. So our lab does genetic workup for research and clinical purposes to diagnose, and also it tailors towards the therapeutics, the precision medicine dream that we all have for genetic diseases. That's what we do in our lab. We also build model system to understand this disease more. And to, regarding motivation, so it's basically genetic disease are mostly pediatric in nature. So all of these kids who are born with these devastating diseases require therapeutic options. At this moment, these conditions do not have any, therapeutic agent that will, reverse the course of the phenotype. So that's why we, look into these conditions from the genetic point of view, how we can revert it back. And this session is amazing because we are going to talk a lot about genome editing and how it relates to the therapeutics of these conditions.
Thank you. Dieter.
Thank you. First, my name is Dieter Egli. First, I would like to thank for being here at this extraordinary meeting in Dubai. I'm an associate professor at Columbia University Medical Center in New York City, United States. It's my first time in Dubai as well as on the Arabian Peninsula, and I'm keenly aware of how privileged I am to get to see this important city that has played not only such an important role in recent history, but also in the more distant past. So my work is focused on early human development. I'm a stem cell scientist, and so I'll look at the very earliest stages of human development, kind of looking for actionable parts where Mohammed works on. Yesterday we were at his center and we saw these enormous gene sequencing machines that can sequence your entire genome. And I'm more focused on what could be done with that information. How could you use that to advance human health? And in particular, I look at the earliest stages of human development. The genome that we receive at conception determines much of your health later in life. What happens in the beginning determines what follows later. And yet, we know very, very little about these early stages of the first steps of human development after conception. And our clinical capabilities to act at that stage is almost in existence, with the exception of a technology that you're going to hear about more from Matt, sitting right next to me. And so I'm a basic scientist, but what really motivates me is the impact that basic science can have on transforming human health. Basic discoveries with broad-ranging impact. And I strongly believe that we are on the edge of what is going to be a transformation of healthcare, so to speak. Today we have a medicine that's largely focused on drugs. Drugs are being taken into one that is more based on editing genes, fixing genes and cell therapies that are the building blocks of our bodies. And so I think I'm very motivated to see the transformation and to help advance it. And I think this is really what the future of medicine is going to be about.
Thank you. Matt?
Thank you very much for the invitation. It's great to be here in Dubai, and I think we were just saying before the session, I don't think I've ever been involved in a conference or session in a room quite as futuristic as this, so thanks a lot for coming. My background is that I'm a medical doctor. I'm a physician and specialist in reproductive medicine. So my background is that I've trained and developed seeing and treating patients that mainly have infertility and want to get pregnant. But alongside that comes IVF, and the first IVF baby who was born and created in the UK turned 45 last year. But IVF's come on a lot since then. And so in my day job, I treat mainly patients with infertility and with IVF, but with the kind of development of genetics and being able to understand and read the genome, we now have technologies such as pre-implantation genetic testing, where you can test embryos to see whether they contain genes for some conditions like cystic fibrosis, for example, and you might choose not to transfer an embryo with cystic fibrosis. But one of the exciting things, and probably the reason for myself being here, is there's only 2 countries in the world that, and the UK being the first and the second being Australia, that have regulation to allow us to do treatment for a condition called mitochondrial disease. And this is, for those of you who don't know what mitochondria are, is they're the batteries of our cells and the powerhouse of our cells. And we always inherit them from our mother. And if you think of a cell, I was trying to think of an example. If you look at the little logo for the future museum, this is your cell on the outside. The purple bit is the nucleus, and inside the nucleus that contains 99.999% of all of our DNA, which is what makes us who we are, and we get half of that from our mother, half of that from our father, and they're packaged in chromosomes. But in the white area is where the cell gets all its energy from mitochondria, and you always inherit those from the egg, from the mother, so you have your mother's, grandmother's, great-grandmother's mitochondria. Now, there are some rare conditions where you have a problem with the mitochondria, and the mitochondria only contains 37 genes altogether. And what happens is, if the mother has that condition, her child may get it, and it can get worse throughout the generations, and to the fact that children can be very disabled and sometimes even die at an early age. So the treatment that's been developed in the laboratory, from labs such as Dieter's, but also in Newcastle, has moved on to a treatment we now do called pronuclear transfer, which involves taking, I suppose, biological material from 3 people: a woman who has mitochondrial disease, her partner, and then the egg from a donor who has healthy mitochondria. And what we do is we fertilize the egg from the donor and from the mother and switch this purple area here between the donor's egg and the mother's egg to allow healthy mitochondria to be passed on. And sorry, I'm taking a little bit of time to introduce myself, but I think these concepts are quite important, because whether we go from just identifying the problems with the genes to being able to screen genes, to be able to do technologies where we kind of, I suppose, edit genes or edit the genetic material, this obviously has implications not just for science, but for society and humanity. And I'm hoping that that's what conversation we're going to have just now. So thank you.
Thank you. And Matt, what motivates you to do that work?
I'm a doctor, so I think the thing that motivates me is it's like a typical question you get asked when you go to medical school: why do you want to be a doctor? And it's like, I want to help people. And genuinely, that is what you want to do, whether you help people with the disease of infertility and not being able to have children, or those that have really debilitating medical conditions. When we have treatments that can start right at the very beginning of life that may prevent disease from happening, that's really what motivates me.
Thank you. Well, what we're going to do, this is a place that celebrates science. What we're going to do is I'm going to try and bring some context into this conversation. And I'd like to use an activity that was first coined by Carl Sagan, the extraordinary scientist in the 70s, and more recently by Janine Benyus, the founder of biomimicry. And I can see Janine's work, so much of Janine Benyus's work around design inspired by nature are evident here in this museum. So I'll invite you to close your eyes for a moment. And this will take just a couple of minutes, but we're going to go on a journey into Earth's evolutionary time. So please ground your feet, close your eyes, or lower your gaze if you're more comfortable. And I'd like you to consider all of Earth's time condensed into one calendar year, where the 1st of January is 4.56 billion years ago, and the 31st of December at midnight is now. So as Earth was forming on the 1st of January, hurtling as rock and gas hurtling through space, it began to form. And it took about 750 million years for the conditions to be perfect for life to evolve on about the 25th of February. Those simple single-celled organisms took a little longer to start a very primitive form of photosynthesis by about the 21st of March, which eventually, over the next billion years, led to the formation of our atmosphere, the removal of carbon dioxide, the release of oxygen. By mid-July is where it gets interesting for today, and that is the evolution of a nucleus. So within those cells, the conditions became perfect for a nucleus to develop. By mid-September, we have the formation of DNA, which ultimately leads to the explosion of diverse, rich, complex life. Early November, we have fungi enriching the soil, cultivating the perfect conditions for the evolution of early land plants and ultimately trees and other plants. We have fish evolving in the oceans that eventually crawl out to become other beings as well. By early December, amphibians, 6th of December, dinosaurs, 13th of December, early mammals, 25th of December at 6:30 p.m, dinosaurs go extinct. Bad day for dinosaurs. 31st of December at lunchtime, 11:30 a.m, hominids, our ape ancestors, stand up and become bipedal. 11:36 p.m, 24 minutes to midnight, humans. 11:59 p.m, 11,000 years ago, 1 minute ago, is the end of the Ice Age, the last Ice Age. And 11:59 and 58 seconds, 2 seconds ago, is the beginning of the Industrial Revolution, 250 years ago. And here we are now, at midnight. The sun will burn out in 5 billion years, or 14 months in this Earth time scale. And here we are now, making decisions that could potentially influence the future of all life, human and all other beings. So when you're ready, open your eyes, come back to the room, and I'd like us to focus for a moment on those moments when genes started evolving. And it's been in this last 30 years particularly that we've, that 0.3 of a second, that we've evolved the capacity to edit genes, to essentially influence our own evolution, which ultimately influences the evolution of all other species, all other living systems on this planet, which compels us to ask not just what and if we can innovate, but why we truly should. And this question sits in the hearts and minds of these extraordinary people regularly, and I'm really interested to hear from you. So as we develop the ability to edit genes for the prevention and treatment of disease, as well as for non-medical purposes, such as for enhancing cognitive abilities, altering physical characteristics, and sometimes what's referred to as even creating designer babies, what are the ethical considerations? How should we address them? What should our policymakers be grappling with as these sciences evolve? And what are some of the potential cultural nuances? And we are just 4 people here. We don't represent the cultures of the world. So I'd like to open it up to anybody who wants to start us off into a conversation, if possible, about some of these matters.
So yeah, that's very exciting journey. We went and came back. So I just want to bring back the DNA, human DNA, the basic building block of humanity. It's a 3 billion base long sequence. So if you look at the 4 bases, SCGT, just think about a sequence of 3 billion of these bases. That's what we are built up. Every cell is packaged with this information. And this is the first time in human history we have this capacity to change it according to our will. It's not just changing it for our generation. If you change it to the germinal cell, eggs, and sperms, you get to change it for the next generation to come as well. So because genes or genetics is actually, it tells you the history, the present, and the future. So if you change a certain element of the genome, it will disrupt all 3 of it actually. Because the future generation will not be able to trace back, if we do the edit, this particular base in the grandparents per se. So there's these ethical issues. Should we do it? So there's a clear case for disease because some of these changes or mutation in the DNA is directly causal for the disease. So we call them, for example, all Mendelian disease, single gene disorders, are directly causal to the, gene mutation are directly causal to the phenotype or clinical manifestation that we see. So there's this strong case to revert it back because it will save lives. It will, not just save lives, economically it's also beneficial. But if you look at the non-medical application of it, so the traits, if you want to change the genome for the purpose of God knows what, but there should be an objective-driven change. We do not know how those change will benefit humanity, increasing traits. For example, I'll give you 2 examples where both has been tried actually. So the first human, prenatal CRISPR was tried 5 years ago in China, 2018. And then the first horse embryo was edited in Argentina 3 years ago. So the first one was done for medical cause, but the horse edit was done to gain the masculinity. So add more muscle mass into the horse. So this is there is no medical benefit, but this is a trait. So we do not know how human will set the objective, but we have the power to change it for disease and traits. So there are ethical issues. Maybe my colleagues will tell you of those more.
Thank you.
Well, that's an excellent summary. I'd just like to pick up on the difference between gene editing the soma or adult cells and the germline. So you mentioned that the germline, sperm and egg, that carries forward to the next generation. So the stakes there are very high. Any change that's being made is permanent and irreversible. So very high stakes. And then there is somatic gene editing, which are our adult cells that will ultimately demise when we ourselves have lived our lives. And so there the stakes are, I would say, because of that, a little less high, but it's also in some ways more daunting because how many cells do we have in the body? 40 trillion? 40 trillion cells. Just imagine that number. You can impossibly change all those cells. So when there is a damage, when there is a problem you would want to do it early. That's how we go about almost anything in life. So if you can edit something, I liken it to, writing a book. Imagine you're writing a book, and you, by inadvertently, one sentence that's really important to you has changed its meaning because there is a mistake. Now it's a lot easier to fix that before a book goes to print. After it goes to print and gets sold and read, it's almost impossible to fix the damage that's done with that. And it's the same for gene editing. At the beginning of development, you have a single cell that is only one that you need to fix. And everything that comes later, would then be fixed as well. So on that note, it makes a lot of sense to really think about germline gene editing. But with that, indeed, we do permanently alter the human species. And so one has to ask the question, for what, right? There is a clear case for disease. And so I'd like to, when thinking about these ethical implications, it is very daunting, but there is an important value of genetic diversity. Nature creates genetic diversity by introducing genetic change in reproduction. And that makes us different from each other. But nature also has no good way to only introduce beneficial variants or variants that are compatible with health. Alongside, it also, as a side product, introduces mutations that cause disease. And the only way nature can remove those is through adverse outcomes. That is, an untimely death or a disease that makes it more difficult to find a partner and have children. And so this is where science and regulation comes in. It is in our fundamental interest to separate those two, to cure disease, to have a direct health benefit to a person, but not interfere with the natural course of nature to create genetic diversity that is so essential for us to function as a species. When we do something, we usually have directional interests. We are thinking about something. But the only interest of natural reproduction is to preserve the species and to prepare it for unknown challenges that are about to come. It's not possible to predict all of that. And so that's why this is my strong own conviction, is that genetic diversity, which would be interfered by design, if genetic editing would be used for designing children, that would have adverse outcomes for that very reason. It won't interfere with the genetic diversity, and we would be less well prepared for the future. In contrast, we can distinguish these adverse outcomes that nature also creates, which is genetic disease. We know what disease is, and we can identify that.
You make it sound so simple, Dieter. It's okay for disease, but it's not okay for traits. But disease is a spectrum as well. So I think maybe most people could agree that perhaps a severe disease that might affect a child and is a lifelong condition like cystic fibrosis, there may be a better case for gene editing. But what about a disease such as Alzheimer's disease? And you might get that, but not until sort of 80s or 90-year-old. Is that really a case to edit the embryo of an unborn child? I think that because there's such a huge spectrum, this is where regulation is actually really important, and it's not for individual scientists or doctors to be making these decisions. It's for policymakers, for societies, for countries to and humanity to be deciding what should this technology be used for and how should it be implemented. One of the things we have in the UK is you can technically do some of these things at the moment just by screening embryos. So by taking a biopsy of an embryo when it's only a few days old and checking the genome and looking for specific mutations and going, well, actually, we know that Huntington's disease runs in this family. will make sure that we don't transfer an embryo back that's going to develop Huntington's disease. And in the UK, we have a panel of, I think, about 600 conditions where you can do these treatments. But for other conditions or traits, as we go across to kind of hair colour, eye colour, that's not something that you'd be allowed to do. So I think it's really important that we have these regulatory frameworks, but also like international, because we have so many different countries. It's possible to actually do the kind of, for example, in the States at the moment, you can do the treatment that we do for mitochondrial disease, but it's not legal to transfer the embryo back again. So what do? Just put it in a shipper and take it to another country where there's not that regulation. So I think like as a world, we really need to kind of come together and create some sort of rules and framework for this technology in the future.
Maybe if I can add to that. So, I mean, that's an important point, Matt. I don't think I have the answers to where to draw that line between disease and what's not a disease or what's justified. I think that's really the call to everyone, no matter what you might be doing, to weigh in on that. That has to be very broadly based, be that clerics or business people or whatever you might be doing here in this room. It requires everybody to weigh in on that. And I think one really poster child example is what was done in the United Kingdom with the mitochondrial replacement to prevent mitochondrial disease. And so there has been a very broad consultation of the public that ultimately resulted in Parliament passing a law that allows this going forward clinically. And I think that's really a model to look up to when it created confidence in the population, in the regulation, that this is going forward for a legitimate purpose. And it also, it allowed education. There needs to be a discourse about these groundbreaking technologies. This cannot just hinge on scientists or medical professionals to go forward with something like that. That requires the broadest possible basis for that.
And I'd like to acknowledge that we will be seeking questions in a minute. So please, if you have some questions, start preparing them. And we'll have about 10 minutes or more to ask some questions. So before we do that, how do we ensure that the benefits of gene editing are accessible to everyone, regardless of socioeconomic status or geographical location? It's the ultimate question in healthcare treatment, but let's see what we can do with it.
So, first of all, just to comment on the ethic issue. Genetic information, as I said, is not particularly private. When you have a certain mutation or changes, it not necessarily changes only you have, your nuclear family or extended family might also have. So that is a very interesting thing, actually, because if that is a disease-causing mutation, so you have to relay that information with your, extended family. So that brings, regulation in place, privacy and all that. So that was my comment on regulation. And genetic, genome editing drugs. This is actually the first week of an approved drug for sickle cell. So in UK, I think they just approved the sickle cell anemia CRISPR-based drug. This is the first one in the world. So what I can tell you from the genome, medicine perspective, the drugs, mRNA drugs that we have for genetic diseases is the most expensive drugs in the world. So Duchenne muscular dystrophy or spinal muscular atrophy drugs, they already exist. These are gene therapy drugs. And each of these, treatment cost more than $1 million. So the accessibility is a very big question. If you look at chemotherapy early in days, it was not accessible for most of the people on the planet. So only the rich high GDP countries were able to use chemotherapy. But slowly and surely, it had it came down, and now it's very much accessible, pretty much most part of the world. So this has to be that scenario. Genetic disease drugs are extremely expensive but it impacts, the global population, not just one population specifically. So that, some of these drugs is just, not even applicable to other population because it's so precise to one population or one family sometimes. And that is not a business case for some of the pharmaceuticals. So what do you do in this scenario? So the government and community have to come into the scene and how to make it a philanthropic effort, not like a pharmaceutical business effort to go for genetic diseases. For example, cystic fibrosis, as Matt mentioned, it has reported 700 mutations, and there are multiple types of cystic fibrosis based on the mutation. Okay, so one drug for one particular mutation might not work well for another types of cystic fibrosis that happen because of a different type of mutation. So all this heterogeneity at the genetic level, all the heterogeneity at the population level makes it very complex to design drugs and accessibility.
I'd like to mention one example of potential application of gene editing, which is for heart disease. Heart disease is one of the most common killers, probably accounting for almost 50% of premature deaths. And it can be managed somewhat with drugs, and of course that means, very perhaps lifelong taking of some drugs. It may also be manageable by introducing protective variants in the genome. That is essentially could either seen as preventing disease or could be seen as a feature. And that's kind of also a case where one has to find that balance between introducing a feature or preventing disease. But gene editing, you essentially have to do it just once, right? So once it's done, and the protective variant against heart disease is introduced, either in the soma or in the germline, that's it. So you wouldn't have to take a drug, right? So drugs can be very expensive, especially if you have to take them over a long time. Of course, it's more profitable, but that's not our interest here as a scientist or as a medical professional. You want to provide a solution. So how do people get to lead healthy lives that, for a lifetime without depending on us?
I just want to kind of take things away a little bit and think about reproduction and reproductive rights. All the technologies we've been talking about here and gene editing and pre-implantation genetic testing relies on IVF. Now, even though I think in the UK about 1 to 2% of all births are IVF births, still most of the 7 billion of us in the world have not come from IVF. And so this all of a sudden, going back to your question about sort of how can we make this applicable to everybody, certainly unless everybody starts reproducing using assisted reproduction, it's not possible. And so that really changes how we look at societies, how we find partners, how we reproduce as a species. I think that's something that perhaps we're not looking at in our lifetime, but maybe 5 past midnight, if humans are still here, then that's something that we can have to consider.
It's interesting. On the airplane over, I watched a film about pods and the formation of babies outside of the uterus. It was quite remarkable. I'd like to open it up for questions. Who has a question? We have several here. We might go 1, 2, and we'll see how we go from there. Thank you.
In reference to what you mentioned about when we are discovering the adverse effects, and in the reference and another mention about the embryo research, what are your thoughts and views about recent initiatives to push the Warnings Commission deadline of 14 days for embryo research to 30 days?
I think that it's a difficult one. Certainly at the moment, most embryos, when they, and this is something that Dieter might be able to answer better than me because I don't do research on embryos, but this is something that obviously has a lot of religious and cultural and societal thoughts about what is the meaning of life. And one thing that I thought was in the last few months, someone's been able to, researchers have created synthetic embryos which have been made from scratch, but essentially look like human embryos. And the thought is, well, actually, you can do testing on those embryos rather than the ones that come from humans. But at the end of the day, it depends on what you view it. Are those cells the same as the ones that have been produced naturally? And surely, if they went on to be developed or implanted into somebody and created a baby, would they be any less than someone who's been created naturally? And I think these raise like really, really big questions about who we are as people, about religion, about society, and there's no right or wrong answer, which often makes this field very controversial.
Well, I perform research on very early development, so the first few days. For me, there was a very convenient time point, 14 days. Many questions can, of course, be addressed in that time frame. But, if for all research, of course, there has to be a justification, right? So how can you explain why you want to do what you want to do? And so I think that has to be looked at on a case-by-case basis as well.
We might use the mic for the audio recording. Thank you.
Thank you so much. And I think that we've been discussing this contradiction for a long time, right? So what is the policy around it? But I think, with all of us who work with patients and know somebody who suffered from something, they really, obviously, the personal pain outweighs any kind of ethical issue around tracing the genetic, or sort of the tree back. And then I don't know if that's something that you've seen and that you encounter, especially for things like cancer. I don't know how far you believe we are away from the editing successfully for cancer and how far that's going to reach the rest of us. But do you see that conflict sometimes where it's, I don't care about the ethics, I just need the cure for my child or my family?
I mean, there are genetic variants that predispose to cancer, like in BRCA1 mutations, various BRCA mutations. There are germline mutations that predispose. I think it's still a very complex disease, so editing, except for these cases, might be difficult. Editing, especially in the germline. Somatic editing, there's a lot of research going on there, how one could engineer cells to detect cancer and then kill them. So it might be more of a cell therapy question than it is a gene editing question.
Yeah, I think cancer, we are moving towards that kind of mentality. Like we really need to bring the therapeutics in place because we are falling behind, and mortality rate for certain cancers we're going up. So and what is happening is the mRNA and gene therapy technology is moving in a direction that's my observation. It's not there yet. Cancer might be a manageable chronic disease in future. It might not be the disease that we know now, because there are models and experiments that shows that you can maybe somehow manage the tumor because it's localized before it's metastasized. It's localized if you intervene early enough with gene therapy or CRISPR genome editing. It might be manageable and make it a more kind of like a manageable chronic disease. So that is coming.
Thank you. Next question.
I will actually ask Matt something you mentioned earlier, on synthetic genetics.
Can you please use the mic?
Sorry, or artificial nature, whatever you want to call it. Over the past decade, we've seen an incredible increase in garage genetics, in rebel genetics, or whatever you want to call it. And I know there are restrictions to a certain degree on what the people can actually get. But if you go back to the 80s, when it's pretty well the same in the computer science, which is everything we have today, more or less comes out of what was being developed at that stage. What are you seeing in terms of regulation on gene clubs and literal, garage genetics where people are playing with all sorts of things, combinations of synthetics with real and so on and so forth? What's the happening on that side?
Thank you.
So I think fortunately, even though we make it sometimes sound simple when we describe it, it's still pretty complex. And speaking to Dieter yesterday, editing a human embryo causes lots of unintentional side effects to the point that it's not really feasible yet to be able to do that. I'm not aware of anyone that can do garage IVF at the moment, but I think that regulators really need to have this on the agenda. Like, we're looking at updating the laws in the UK. We have the Human Fertilisation Embryology Act, but it specifically looks at 2 specific techniques for mitochondrial replacement, pronuclear transfer and mitochondrial spindle transfer. And that's 2 very specific technologies. And if something comes along in a year or two's time that's completely different, even for the same disease, there isn't the regulatory framework there. So I think policymakers need to think about, when creating laws and regulation, about trying to future-proof it and looking at perhaps principles that could apply to new technologies.
Thank you. There's a challenge for futurists in the audience, is how to grapple with these global cultural and moral and ethical concerns. We've got one more question at the front here, and then Sarah, I'll come to you at the back.
So I think I want to look at the question a little bit more broad. When we look at health, it's very, very narrow, but we see something like gene editing is happening across all spectrums. So you see it across different species, flora and fauna. So one question is, there's a lot of these open databases currently available on gene pools, and is that a danger for future? How do we protect it at the research stage? And secondly, a lot of the technologies, especially CRISPR right now, you can buy some of these technologies. I am aware of a paper where someone created a virus, for example. So can these be targeted specifically at populations?
Thank you.
I think the first question is how to safeguard the public databases. So I think there enormous initiative went into it, to putting multiple IRB ethical restrictions to get genetic data, but again, you have to also bring the data into public domain, because it will hamper the global discovery initiative. And as my colleague mentioned, genetics, we are diverse, individuals. So if you do not know how this variant is impacting this population versus the other, it might create a problem. So for example, I'll give you an example. G6PD deficiency, it's a metabolic disorder that we see in most in Asia. It's almost non-existent in Caucasian population, but we would have had not known unless we looked at the interglobal database. So that's kind of a beneficial side of it. But again, there's also the other side of it is it's not representative yet for every population that we see in the planet. So if there is an initiative to, say, design drugs for cancer based on those databases, I was looking at it, I gave a talk on this issue. The 90% of the cancer data are coming from Caucasian individuals. So if you make an AI model to predict or design a molecule, synthetic molecule, to target an mRNA that is faulty and may cause cancer, that blueprint is coming from one population. There is no way of moving forward globally in that scenario. So you have to bring all this data from all this population to enrich the databases. And for viruses and all that, yes, you really can target for sure, because certain DNA template is predisposed to certain type of virus infection that has been shown. So you have to know that causation before getting into targets. So that's already in research for different populations.
If I could just add to that, I think Muhammad told us yesterday about his project about the pan-Arab genome. And I think this is really important to capture the genetic diversity of different populations. And so congratulations, and it's a very important effort. And much of the research in the past has, of course, been focused more on Caucasian people like myself. And so diverging away from that is very, very important. It is so good to see that these efforts are happening right here, right now. And generally, the way genetic information is protected is often, to come to your question, is often that the information is completely dissociated from a name. So there's no name associated with the genetic information, so it becomes very hard to figure out from where that comes from. That doesn't mean it's completely impossible, but it requires serious genomics and genetic skills to do so, and a lot of time for something that really has no benefit. And in addition to that, people who participate in such research or work and donate themselves for genome sequencing, they are made aware of those risks that there could be is the potential for disclosure. And so they consent to that type of risk before they make that donation. So that's kind of how it's structured.
I want to add one more. I'm also Canadian, so I take pride to that fact that Canada is one of the first countries that introduced a non-discriminatory law based on genetics. So if your genome have a certain disadvantage in terms of disease or so, your employee or certain other entities cannot discriminate you based on your genome. So all of these needs to be taken into consideration. So when public database become available to everybody, all of this information becomes handy even for the medical insurance companies as well. But regulation is becoming important. And also, if you look at certain countries, they don't want to sequence themselves or protect themselves. It's not going to work anymore. I'll tell you one example. So from Arab Genome Initiative, what I learned that there is a kind of like a taboo to sequence Arab genome. But then I realized New York City have more Arab genome than anybody in the world. So what is the point of not knowing the genome here in this region rather than somewhere else? So those initiatives needs to be funded, and those initiatives needs to be scrutinized, and of course there should be proper ethical boundaries set in place that is in line with the culture and of the country.
That's probably a beautiful note to finish on. Proper ethical boundaries need to be in place for the ethical consideration of this work. I know there's more questions. There's more questions.
I have one more question for you. So will we get another year?
Will we get another year?
Yes, as humanity.
This is a good question. And my favourite subject. So we are in this rite of passage, right? We don't know how it's going to turn out. So the question that I sit with in everything I do, from drinking an oat milk latte to coming and flying across the world to be at an incredible meeting like this, is what is it in service to? And so I'd like to leave you with that question. What is it in service to? And there's not one answer, there's trillions and billions of answers, but it is something that we are now, because we can see it all suddenly, with big data and other technologies, we can suddenly see it all. We are the generation that are sitting with this complexity, with more influence than any past and possibly any in the future. We are the adults that are doing this work now. So I'll leave you with that question. What is it in service to? And please help me in thanking these wonderful panellists.
Thank you.